Imagine a world where the very imperfections in materials become their greatest strength. This is exactly what researchers at Rice University have uncovered, leading us into a new era of ultra-efficient electronics. They found that microscopic wrinkles in atomically thin materials can manipulate the spin of electrons with unprecedented accuracy, paving the way for incredibly compact and energy-efficient devices. Typically, today's gadgets rely on the flow of electrons through silicon to process and store information. However, the future of computing might lie in a different realm: spintronics. This emerging field leverages a quantum property of electrons called spin, which can be either up or down. By using spin, we could potentially overcome the limitations of traditional silicon-based technology, significantly reducing the energy consumption of devices and data centers, at a time when global energy use, driven by computing, is skyrocketing. But here's where it gets controversial. Spintronics faces a significant hurdle. The information encoded in electron spin tends to degrade quickly, often lost when electrons scatter and collide with atoms. In a groundbreaking study published in the journal Matter, Rice University materials scientists have discovered a solution to this problem. They found that by bending atomically thin layers of materials like molybdenum ditelluride, they can create a unique spin texture known as a persistent spin helix, PSH. This PSH can maintain the spin state even during scattering collisions. In conventional materials, the spin of an electron is closely linked to its momentum, so any change in direction can alter the spin, explained Sunny Gupta, a Rice alumnus and postdoctoral associate who co-authored the study. However, in materials with PSH states, the spin remains constant, regardless of the electron's movement. This is a rare and challenging property to achieve, as very few materials naturally support PSH. The research team, led by material scientist Boris Jakobson, hypothesized that the wrinkles and folds in 2D materials could be the key to controlling electron spin. When a 2D material is bent, the top layer stretches while the bottom layer compresses, creating an uneven strain. This strain causes positive and negative charges to shift slightly, generating an internal electric field, a phenomenon known as flexoelectric polarization. In a bent 2D material, the electron spins interact with this flexoelectric effect, causing spin-up and spin-down electrons to separate into distinct regions. The stronger the curvature, the more pronounced this effect becomes. At its peak, the curved regions produce a powerful effect that aligns the electron spins in a helical pattern, flipping between up and down states over a distance of just about 1 nanometer. Wrinkles and folds are common in 2D materials, often appearing as self-sustained hairpin-like loops with extremely high curvature, Gupta noted. Our experiments show that in these hairpin folds of molybdenum ditelluride, PSH states can achieve a spin precession length of about 1 nanometer, the shortest ever recorded. This short precession length means that spintronic devices can be incredibly compact, which is a game-changer for the industry. This work demonstrates that controlled bending of 2D materials can be used to engineer unique and exotic field profiles, said Jakobson, the Carl F. Hasselman Professor of Material Science and Nanoengineering at Rice. A simple mechanical pinch, which is easy to apply to 2D materials, can split the spins and induce PSH texture. Gupta emphasized that the initial premise of the study was somewhat counterintuitive, as quantum behaviors and elastic mechanics are typically considered separate domains of physics. We've shown that macroscopic changes in the shape of 2D materials can influence deep quantum relativistic interactions between electron spin and nuclei, he said. This discovery opens up new possibilities for creating exotic spin textures that could revolutionize spintronics. And this is the part most people miss. The potential applications of this research extend far beyond just theoretical interest. As we continue to push the boundaries of what's possible in electronics, innovations like these could lead to devices that are not only more efficient, but also more sustainable. What do you think? Could this be the breakthrough we need to tackle the growing energy demands of our digital world? Or is there still a long way to go? Share your thoughts in the comments below.